So now let's look at other mechanisms of growing DNA for different purposes. So in this case, let's look at maybe we're trying to get DNA from a patient and we want to replicate specific regions on their DNA so that we can then run tests to see if they have certain mutations that are associated with certain types of cancers or other diseases. Or maybe we're working a crime scene and we're getting DNA from the crime scene. So, you can see this over here. Um, they're grabbing DNA from some crime scene here, and then they're going to use that DNA. They have to replicate the DNA so that they can then run tests to see if it matches certain individuals. So I sound like I'm the one who did this with scientists back in the 80s, specifically this man here, Dr. Kerry Mullis, figured out a way to grow DNA without cells. And he called it the polymerase chain reaction. And, it's always interesting to hear the stories about how scientists come up with these things. So he was out surfing, kind of doing his thing. Maybe he was doing drugs, maybe he wasn't. We don't know. It doesn't really matter because you know what? What matters is that his brain just went poof and he was like, hey, here's an idea. And he came up with this way to replicate DNA replication, but without cells. So instead, he used little test tubes and he added the DNA that he cared about with the different nucleotides, with primers, with DNA polymerase, and with all the buffers that he needed. He then used this type of machine. So it's a 3-sectioned hot bath that can be, it's temperature dependent. So each of these can be held at certain temps that differ. So about 92 to 95 degrees, about 54 degrees, and then about 72 degrees. Okay. And he or his assistants would transfer the DNA or the tubes from one bath to the next bath to the next bath and back, and then go again, and then back and go again, and then back. And this was able to replicate DNA really fast without using cells at all. And then he was able to, because he could replicate the DNA, he then could run it on a gel. So this is what this is supposed to indicate is our gel. Here we have DNA from 2 patients. Here you see lots of different segments. This one, there was no DNA amplified. So patient A is positive for some certain disease where patient B is not. This might be a reason that you might use gel electrophoresis. And he could do this in just a few hours versus waiting for days for the bacterial cells to replicate because you had to get the DNA into the vector, get the vector into the bacteria, allow the bacteria to grow. Then you had to select the proper bacteria, pull them out, and then just grow those guys. And then you could run the tests. So now we're doing it in like a day. We have everything done and we can look at the results. Super fast, super awesome. And so the steps of PCR, so really quick, this is what they used to use. Eventually they got a PCR machine called a thermocycler that was able to run everything on its own, which is a lot nicer. So you didn't have to move the DNA around all the time. So there was 3 steps to PCR: denaturing the DNA at about 95 degrees Celsius. You then allow the primers to anneal at about 52 degrees Celsius. And then the primers are going to dictate where RNA or where DNA polymerase binds. And so what section of DNA is going to be replicated. And then you extend the DNA at about 70 degrees Celsius. So DNA synthesis occurs. and then you heat it back up to allow everything to denature, and then you anneal and then extend. We use heat-stable Thermus aquaticus, Thermus aquaticus polymerase, because so that's called Taq polymerase, because it doesn't break down at 95 degrees Celsius, whereas human DNA polymerase did. So every time you would heat the DNA up to 95 degrees Celsius, you would kill the DNA. You'd denature the DNA polymerase. And so every time you'd have to add new DNA polymerase. So with heat-stable Thermus aquaticus polymerase, we don't have to do that. And so here you see the red strand up here and the blue strand. Those are the parent strands. Those are called the long strands. Here we have the primer anneals here and the primer anneals here, and we produce medium-stranded DNA from all the long strands. When the DNA all denatures again, the long strands will produce medium strands again. Medium-stranded DNA, which you see here and here, so that's this one and this one, are going to produce just the target DNA that we care about, just that small section, okay? So they produce small strands. And then DNA is all going to denature again, and you're going to allow the primers to anneal. The longs are still going to produce these mediums. Mediums will always produce these smalls, and the smalls will also produce smalls. So we end up with lots of small stranded DNA by the end of the 23, 24, 32 cycles that we go through. And so here you can see all the DNA that has been produced. Typically, 30, 34 cycles are about the norm. And once you have that, you have mainly these small strands of DNA that we care about. So I do want to play this video because I love it. It's one of my favorite videos. Those of you who were ever around in the 80s, which is probably not a lot of you, but those that were will appreciate this song as well. I feel like SpongeBob 4 hours later. There was a time when to amplify DNA. You had to grow tons and tons of tiny cells. Oh, and as long as I got to get but you can amplify in vitro just as well. Just picture top of where the bottom is. Nucleotides and polymerases too. Denaturing, annealing, and extending. Well, it's amazing what heating and cooling and heating can do. PCR, when you need to detect mutations. PCR, when you need to recombine. PCR, when you need to find out who the daddy is. Who's your daddy? PCR. When you need to solve a crime, PCR. When you need to detect mutations, PCR. When you need to recombine, PCR. When you need to find out who the daddy is, Who's your daddy? PCR. When you need to solve a crime. Solve a crime. PCR.
Biolab salutes you with the all-new 1000 series thermal cycling platform.
Ingenious. I would buy one just because of that video. It was that awesome. Not going to lie. So, favorite song there. So, almost every time in my exams, I will give you a sequence of DNA, and I say, okay, if you start out with 5 long strands, how many strands of DNA, maybe small, medium, or large, well, probably not long because long stays the same, but total, small, or medium, I might ask all of them at the end of some certain cycle. So we're amplifying DNA, we're doubling the number. So every time we go through a cycle, we're going to double the total amount of DNA there. And we know that longs always produce mediums, mediums always produce smalls, smalls will produce smalls. So at the end of one cycle, you had 5 long strands of DNA, you're going to produce 5 medium strands from that. 5 plus 5 is 10, so we know that. So if we do it again, now you have these 5 strands, these long strands are going to produce medium strands. These medium strands produce small strands, but these medium strands don't go away, so they're going to move over as well. So now you have 5 plus 10 plus 5. Here we have 5 long strands of DNA producing those medium strands of DNA. These 10 medium strands of DNA are going to produce 10 small strands of DNA. These 10 medium strands move over. 5 medium strands here, or these 5 small strands here, are going to produce 5 small strands of DNA, but the 5 strands that were here are also going to move over, so that's 10 more. So now we have 20 small strands. And again, 5 plus 15 is 20, plus 20 is 40. Do it again. 5 long strands produce 5 medium strands. These 15 medium strands produce 15 small strands. These 15 medium strands also move over. 15 plus 5 is 20. And now we have 15 down here. 20 small strands produce 20 new small strands. So that's the 15 plus the 20 is 35. Plus these 20 move over, which is going to give you the 55. And that brings us to 80. So the easy way to do this is we always know that we're going to double our total amount of DNA. 5, 10, 10, 20, 20, 40, 40, 80. Okay. If we go again, it'd be 160. If we go again, it'd be 320. If we go again, it'd be 640. And on and on and on. It's always doubling. We never change longs because the long-stranded DNA is what we added initially, and we never add more. So that's never going to change. And if you notice, there's a pattern here. The medium strands go up by whatever the long strands are. So if we start out with 5 long strands, medium strands go up by 5. 5 plus 0 is 5. 5 plus 5 is 10. 5 plus 10 is 15. 5 plus 15 is 20. If this was 9 strands, 9 plus 0 would be 9. 9 plus 9 would be 18. 9 plus 18 would be 27. Then we'd be going up by 9. So whatever our long strands are, we're going to go up by that every time. We just add that to what we have already. And then, since we know these two numbers, if we take these two numbers and we subtract them from the total, we get our smalls. 20 plus 5 is 25. Subtract from 80, that would be 55. See? So once we do that, now we can run this. Now we can run this DNA that we just produced on a gel. So we use electrophoresis to visualize our DNA. The electrophoretic gel typically has some type of radioactivity in it, like we might use ethidium bromide, which is radioactive and will glow under UV radiation. Or we might add a DNA probe to the sample to hybridize with our DNA that we care about so that we can see it glow. Either way, it will work. We run it on a gel. The gel is in a solution. The solution is an electrolyte solution. We have a negative charge at the top where the DNA is inserted. DNA is negatively charged, so it's going to move away from the negative charge and pull towards the positive charge. Once we're done, we can then read the DNA. So the first one is always a size marker, and then we have information for each of these. And we look at where the DNA settles out. Longer strands are going to settle out earlier. Shorter strands can move through the gel a little easier, and so they're going to settle out farther down. This is what I just said. So here's my DNA, and an example might be you have the size marker, you have victim's DNA, you have a criminal DNA, and then you have two suspects, okay? So here's what the DNA looks like. Here are the size markers. Here you have your victim DNA. Here's criminal DNA, and then you have one suspect here and another suspect there. So suspect 1 obviously can be excluded, but suspect 2 cannot be. Because he has the same DNA as the criminal. Now, you can use the same thing as a potential mutated gene. In this case, 2 might code for a non-mutated gene, 3 might code for a mutated gene. And then patient 4 has a normal and a mutated gene, whereas patient 5 has just a mutated gene. So if this is a completely dominant gene, then both patients would have the disease. But if it is a recessive, then patient 4 would be considered a carrier. And patient 5, or this patient, would be a carrier. This one would have the disease. So I have some questions here. I'll put them up. If you have troubles with any of these, I'm not going to give you the answers off here. But if you have troubles with these, then you can bring them to class, okay? Here's the next one. I actually have the answer to this one on the next slide. I want you to know how to do it. So here's how you would do it. This is how I would do it if I were you, okay? 2 more questions. Again, if you don't know the answers and you need help, come to class and ask. One more questions. All right. I'm going to stop the lecture then. I'm done. I'll have all these posted. You have a wonderful day. Goodbye.